Right, so the law of sines is one of two rules that we're going to use when we're trying to solve triangles that are not right triangles. So far, we've just been looking at right triangles, which means we can use sine, cosine, and tangent, all of which talk about the ratios between sides of a right triangle. We also have the Pythagorean theorem, which lets us set sides of a right triangle equal to each other in some way. But those rules only apply as long as we're working with a triangle that has a 90-degree angle in it. So in the next two topics, that being the law of sines this week and the law of cosines next week, we'll be looking at solving non-right triangles. So the law of sines, as it's stated, is another ratio. And it says that the sine of angle A divided by side A is equal to the sine of angle B divided by sine B, which is also equal to the sine of angle C divided by side C. So we're going to use some of those ratios in order to solve a given triangle. And when we have a problem that says, solve a triangle, that means find all 6 identifying factors of the triangle. So all 3 angles and all 3 side lengths. So in practice, that really means just finding 3 pieces, since in order to have a solvable triangle, we'll need to know 3 of the things first. So let's get started. In problem 1, we're told that angle A is 75 degrees, and side B is 7 inches, and angle B is 20 degrees. So we may as well start by solving for angle C. So since I already know 2 angles, I'm just going to solve for the third one right away. So angle C, which is the only missing piece, should be 180 degrees minus the other 2 angles, 75 and 20 degrees. Since I know that in a triangle, all 3 angles must add up to 180 degrees, which means that C, in this case, must be equal to 85 degrees. Next, I need to find my 2 missing side lengths, which are side A and side C. So start by looking for side A. And I'm going to need the law of sines in order to get that. So I'm going to say that A divided by the sine of angle A, which is 75 degrees, is equal to B, which is 7 over the sine of angle B, which is 20 degrees. And use that equation to solve for A. Meaning that A is equal to 7 times the sine of 75 degrees divided by the sine of 20 degrees, which is equal to 19.8 inches. Since I want to use the same units that our given side is in. And finally, let's come up with side C. So C over the sine of angle C, which we calculated to be 85 degrees, is equal to 7 over sine 20. And when I have the choice of which ratio to use out of the law of sines, since there are 3 of them, I know I'm going to need to use the ratio that contains the piece that I'm looking for, which in this case is side C. But I'm going to want to set it equal to the ratio that I know the most about, which means hopefully going back to the given information. I was already given everything about letter B, both side B and angle B, so I'm going to refer back to that ratio rather than the one with A. So solving that equation for C, I get that C is 7 times the sine of 85 degrees divided by the sine of 20 degrees. And that is equal to 20.4 inches. But finally, we're going to get the area of this triangle using any one of the area formulas that we have. So 1/2 AB sine C seems like it will work. Notice that in that case, each of the area equations features each letter once. So 2 sides and an angle. So whichever 2 sides I pick, I'll want the third angle when using that. So I'll use 1/2 AB sine C, which is 1/2 of 19.8 times 7 times the sine of 85 degrees. That is equal to 68.9 square inches. In part B, we'll look to do the same. Since I know 2 angles, I'm going to start by looking for my missing angle first. So angle C should be 180 minus 16 minus 102, meaning that C is equal to 62 degrees. All right, next we'll look for side A. So A over sine 16 is equal to 5 over sine 62 degrees. Since I'll need to use the ratio with C because that's the one that I know everything about. So A is equal to 5 times the sine of 16 degrees divided by the sine of 62 degrees, which comes out to 1.56 meters. Then to look for side B, do B over the sine of 102 degrees is equal to 5 over sine 62 degrees again. So B is equal to 5 sine 102 divided by sine 62. And that is equal to 5.54 meters. And then lastly, we'll want to get that area where we'll use any one of the area equations that we like. But let's choose one that involves side C, since we're given side C in the beginning. So how about CA sine of B? So this will be 1/2 times 5 times 1.56 times the sine of 102 degrees. And that works out to 3.81 square meters. Part C is a little different. So in part C, we're given two sides and one angle, meaning that we can't solve this one the same way that we started initially, because I only know one angle. And in fact, this is going to give us a bit of an interesting decision to make. But we can start off by using the law of sines directly to find our missing angle, which in this case will be angle A. So I'll do sine A divided by 34 is equal to the sine of 36.5 degrees divided by 24, meaning that sine of angle A is equal to 34 over 24 times the sine of 36.5 degrees. And if we were to look at the unit circle for a moment, there would be two angles for A that would satisfy this ratio. Since I can find an angle that's either in the first quadrant or the second quadrant, meaning I can find both an acute angle and an obtuse angle that would plug in for A and have this equation come out true. Which means, based on the given information provided, where there are two sides and one angle, I could end up with two different triangles that solve the given information. So we're going to have to identify both of them. I'll start by looking just for angle A1. I'll label each of these with a subscript 1 because I want this all be the first triangle. And A1 works out kind of the way we'd expect. We'll take the inverse sine of the other side, of each side, I should say, 34 over 24 times the sine of 36.5 degrees, and get 57.4 degrees. Solving for our other missing sides, or our other missing pieces, let's start by getting angle B, which we'll call angle B1. That should be the difference between 180 and our other angles, 36.5 and 57.4, which is equal to 86.1 degrees. And we'll solve for our missing side, which is B1, or side B, which we'll call B1, and we're going to need the law of sines again to do that. So side B divided by the sine of angle B, 86.1 degrees, is equal to whichever other ratio we'd like. We'll probably use C in this case since that was given. So that ratio should be 24 divided by the sine of 36.5 degrees, giving us B1 is equal to 24 times the sine of 86.1 degrees divided by the sine of 36.5 degrees. And we get 40.3 centimeters. And that is all based on the assumption that angle A was equal to just the sine inverse of that number on the right side at the beginning. So assuming that our angle A is an acute angle, something in the first quadrant, this is the triangle we get. So that means we have to check to see if we have a second triangle that works. So to get that other starting angle, I wanted the one that still solves sine of A is equal to that number, which means that this angle should have the same reference angle as A1, but it will be in the second quadrant. So A2, which was the other option for A, should be equal to 180 degrees minus angle A1, which we found to be 57.4 degrees. Making that subtraction, we get 122.6 degrees. And now we'll do the same work again to get an angle B2 and a side B2, but based off of angle A2 being 122.6 degrees instead of A being 57.4 degrees. So B2 then should be 180 degrees minus the given angle, which is 36.5, because that information cannot change. Everything that's been written down in black was all of the given information, and that stuff doesn't change. This time, instead of subtracting 57.4, we'll subtract 122.6. And as a result, we get that angle B is equal to 20.9 degrees. And then we'll solve for side B2. So B2 over the sine of 20.9 degrees is equal to 24 divided by the sine of 36.5 degrees. Because again, I'll come back to that given information. So B2 is 24 times the sine of 20.9 divided by the sine of 36.5. Plug that into a calculator and we get 14.4 centimeters. And then each of these two triangles will have their own areas, so we'll solve for them independently. On the right side, we'll call it area 2. Since our given information has both side C and A, I'll use the area equation that uses those two sides. So 1/2 CA sine B, which is 1/2 of 24 times 34 times the sine of 20.9 degrees, which comes out to 145.5 square centimeters. And we'll look for the same thing for that first triangle on the left. We'll use that same formula. 1/2 CA sine B. So 1/2 24 times 34 times the sine of angle B, which in this triangle is 86.1 degrees. And that comes out to 407.1 square centimeters. And in part D, we're again given two sides as our given information. So the process looks pretty similar to part C at the beginning. I'll start by looking for the missing angle out of the given information. So that missing angle should be angle C, since I know side C is 12, and I know both pieces about letter B. So this is sine 96.2 degrees divided by 10. So sine of C is equal to 12 over 10 times the sine of 96.2 degrees. If we plug that into a calculator, we get that the sine of C is equal to 1.193. And we run into a bit of a problem here, because we have that sine of C is equal to a number that's bigger than 1. So we end up getting no solution here. Which means that in the case of if we're given two sides and an angle, then it's possible that we could have two different triangles that solve the same given information. But we could also end up with given information that doesn't add up to a triangle. Because we'll find that these two side lengths aren't quite long enough to connect if that angle B must be 96.2 degrees. So no solution to this particular triangle. All right, better end it here.